Hi, everyone. Today, we're excited to introduce our CVPR 2026 paper, PropFly, Learning to Propagate via on-the-fly supervision from pre-trained video diffusion models. This work is a collaborative effort by co-first authors Wonyong Co and Jaeho, and co-corresponding authors Jaehyup Lee, Soo-Yi Kim, and Munchurl Kim. Editing videos with text prompts often struggles with precise editing. With propagation-based editing, you get total control by editing a single frame, like our panda here, and letting the model handle the rest. It's the key to achieving high-fidelity, fine-grained visual edits across an entire sequence. The primary challenge in this field is the extreme scarcity of paired video datasets needed for training, which must consist of a source video, an edited version, and a matching text prompt. While existing synthetic datasets like Senorita 2 million try to bridge this gap by using text-guided video editing to generate pairs, this method comes with heavy computational costs due to the diffusion process, particularly at high resolutions. This inefficiency leads to limited scalability and a lack of variety, as the model is restricted to predefined pairs and a narrow range of transformations. To solve these issues, we introduce PropFly, a novel pipeline that generates high-quality data pairs on the fly during the training process. Our solution begins with a technique called one-step clean latent estimation. Instead of the traditional full diffusion sampling process which requires around 50 iterative steps and is far too slow for real-time training, we predict the velocity field from a noisy latent and approximate the clean image in just a single step. While this approximation might lose some fine details, its incredible speed is what makes on-the-fly data generation possible during the training loop. To create our training pairs from this estimation, we introduce CFG scale modulation. Classifier-free guidance allows us to control how strongly a text prompt, like, a bear walking in snow, influences the resulting video. By applying a low CFG scale, we generate a source latent that closely maintains the original video's structure, and by applying a high CFG scale, we produce a target latent that reflects the full transformation of the edit. This clever modulation allows PropFly to synthesize diverse source and target pairs instantly from a single noisy input, eliminating the need for any pre-computed datasets. PropFly's training pipeline is built around three core stages that work together to eliminate the need for pre-computed paired datasets. It begins with data sampling and random style prompt fusion, or RSPF, where we take a video text pair from a dataset and fuse the text with a random style prompt to create a highly diverse augmented prompt. This leads into the on-the-fly data pair generation stage, where we utilize a frozen video diffusion model to instantly synthesize a source and target latent pair simply by modulating the CFG scales. Finally, in the guidance-modulated flow matching stage, we train a specialized adapter by guiding its predicted velocity field to match the semantic transformations found in our high CFG target. This entire end-to-step process allows the model to learn complex video propagation tasks with high effectiveness and guidance. Let's zoom in on the first step in our pipeline: random style prompt fusion, or RSPF. We begin by sampling a video text pair from a standard dataset, but we don't stop there. To provide diverse video editing samples, we randomly select style prompts from a vast set that includes weather, artistic styles like Van Gogh, materials, and even specific backgrounds. By simply concatenating these styles, for example, adding "in snow" to "a bear walks," we create an incredibly diverse range of training scenarios. This variety is essential because it forces the model to learn robust transformations across a wide combination of content and styles. Furthermore, this strategy is a powerful way to further leverage the text-to-video generation capabilities already inherent in pre-trained video diffusion models, allowing us to tap into their rich semantic priors for more effective training. Now, let's look at how we actually synthesize the training pairs using a pre-trained and frozen video diffusion model. From a single noisy latent, we predict two different velocity fields by varying the classifier-free guidance scales. A low CFG scale results in a source latent that preserves the original video's structure, while a high CFG scale creates a target latent that reflects the full semantic transformation of the augmented text prompt. This allows us to generate a complete source and edited video pair on the fly for every training iteration. It's an incredibly efficient way to provide the supervision needed for propagation-based editing without any pre-computed data. To effectively train our model, we introduce a specialized guidance-modulated flow matching loss. We attach a trainable adapter to the pre-trained VDM and feed it both the entire source latent for structural guidance and the first frame of the target latent for visual style guidance. Instead of using a conventional flow matching loss that would simply try to reconstruct the original video, our GMFM loss guides the predicted velocity to match the VDM's high CFG velocity field. This specifically teaches the adapter how to associate the visual style of an edited first frame with the complete semantic transformation required for the rest of the video. The qualitative results clearly demonstrate PropFly's superiority across various editing tasks. For local object changes, like turning a camel into a horse or a black swan into a paper boat, our model maintains sharp details and smooth motion. When it comes to global background and object changes, such as transforming a bear into a panda in a snowy bamboo forest, PropFly preserves the original movement while applying realistic environmental effects. We even excel at complex style transfers, like turning a walking person into a robot in a ruined city or creating a cyberpunk-style camel. Compared to methods like any V2 volts and Senorita 2 million, our approach shows significantly better fidelity and temporal consistency. PropFly also outperforms across major benchmarks. On Editverse Bench, our 14 billion parameter model achieved state-of-the-art results, leading in both PIC score for video quality and clip scores for text alignment. We see the same trend on the TGVE benchmark, where PropFly consistently outperforms both text-guided and propagation-based competitors in temporal consistency and semantic accuracy. These results confirm that our on-the-fly training strategy effectively captures the complex dynamics required for high-quality video editing. The strength of PropFly comes down to 3 core innovations, which we've validated through extensive ablation experiments. Our ablation studies highlight 3 critical factors. First, by using one-step clean latent estimation instead of iterative full sampling, we avoid numerical errors that lead to motion misalignment between training pairs. Second, while standard flow matching simply tries to reconstruct the original video, GMFM guides the model to learn the actual semantic transformations introduced by high CFG scales. Finally, our RSPF strategy provides a rich variety of content and style combinations. This ensures the model generalizes far better to complex real-world cases compared to models trained on static, pre-computed datasets. In conclusion, PropFly introduces a novel training pipeline that redefines propagation-based video editing. By leveraging on-the-fly data generation through CFG scale modulation and one-step latent estimation, we completely eliminate the need for expensive, pre-computed training data. Our RSPF strategy and GMFM loss ensure high fidelity, robust transformations, and superior temporal consistency across a wide range of editing scenarios. We believe PropFly sets a new standard for controllable and scalable video editing. Thank you for watching, and feel free to check out our paper for more details.